Okay, so now we're going to prove that concatenation is associative, which means if you're concatenating through this together, it doesn't matter if you do the first two first or the last two first. Okay, so notice all the quantifiers. We want to prove for all xs, for all ys, for all zs, xs concat ys concat zs is the same as xs concat ys concat zs. So that's our goal. We know this entire statement here in the middle is P of s. So we want to prove for all xs, P of xs. Okay, so how are we going to do that? So we did the same as we did before. We have to prove it for the base case, which is empty list, and we have to prove it for the step case. So the base case, we have to prove P of the empty list, which is for all ys, for all zs, all the statement here, but xs replaced with the empty list. Empty concat ys concat zs equals empty concat ys concat zs. Okay, that's my goal. So I'm going to let ys and zs be arbitrary and prove it's true for any choice of ys and zs. So we'll take the left hand side first, which is empty concat ys concat zs. What's that equal to? Let's have a look at my rules. I know empty plus ys is ys by a1. So this is just ys plus zs by a1. And now what I'm going to do is, instead of going all the way to the right hand side, I'm going to start with the right hand side here and try and manipulate it so it looks like the left hand, looks like this term here. Sometimes it's easier to work from both sides and get to the middle rather than work from one side to the other side. That's what I'm going to do here. So the right hand side is empty plus ys plus zs, which by rule A1, empty plus anything is at anything. So the empty goes away and we have ys plus zs. Ys concat z, I should say, by A1. So therefore the left hand side is equal to the right hand side. Okay, so now the step case. We want to assume for xs is equal to some arbitrary list, say ws. So I want to assume for xs equal to ws, p of ws. So I want to assume this whole statement is true. This whole statement here is true for some arbitrary ys inserted instead of xs. So we're assuming that for all ys, for all zs, ws concat ys concat zs is equal to ws concat ys plus zs. Okay, that's my assumption. And now I want to prove for any new element w, this whole statement with the w cons onto the ws. So I want to prove for all w, for all ys, for all zs, w cons ws plus ys plus zs is equal to w cons ws plus ys plus zs. Okay, so I want to prove this whole statement here. So let me just move my rules sheet over, get it out of the way. Okay, so now I'm going to let w and ys and zs all be arbitrary. Let w, ys, zs be arbitrary. Okay, and so this is the statement here we want to prove. Again, we should notate our inductive hypothesis. So our assumption here, we give it this new name IH because of the inductive hypothesis. So we want to prove this thing here. Let these terms be arbitrary. Start with the left-hand side, which is equal to all this stuff here. W cons ws plus ys concat zs. Okay. So what can I use to help me here? I can use the rule A2. So I can take the w out of the cons here. So this is going to be w cons ws concat ys concat zs. That's by rule A2. And now we can note ws concat ys, this thing here, this is just one list, right? So once again, this is in the form for A2 to apply, because this is true for any list XS. Whatever WS concat YS is, this whole thing is a big list, right? So I can do the same thing again. I can take the W at the front. So we W cons onto WS concat YS concat ZS. So just take the W out front using A2. And now this term here looks just like my inductive hypothesis, so I can swap the brackets over. So you have W cons WS concat YS concat ZS by inductive hypothesis. And at this point I'm going to stop and then try from the right hand side and see if I can make the two terms match. So the right hand side is this term here, W cons WS concat YS concat ZS, and by A2 I can take the W at the front to get W cons WS concat YS concat ZS by A2. And we know this term here is the same as this term here, therefore the left hand side equals the right hand side, and so the statement is proven. So therefore we know for all XS, for all YS, for all ZS, if you do the concatenation first here and then afterwards, or first here and then you do the XS, these two things are going to be the same, which is what we expected. I could have also, at this stage here, run the rule A2 backwards. So because Haskell's a pure functional language, you can treat this equality just like the equality for formula. So I can replace anything that looks like this with terms that look like this. So I could have done it this way, or I could have just directly put the W back in again. So I can have W cons WS concat YS concat ZS by A2, and then this term here looks exactly like this term here. So this is now equal to the right hand side. And then I could have avoided doing these two steps if I really wanted to. Either one is fine. Now, the other thing I want to quickly talk about is how do we know to induct over XS and leave Y and Z arbitrary? And the reason is, if we have a look at the definition for concatenation, it's got two variables, and it seems to be recursing on the first variable, right? So usually the variable that's being recursed over is getting one smaller each step. That's the variable you want to do induction over. So here, XS is the first list in this equation in both terms, so it's probably the thing I want to do induction over. This is just a rule of thumb, and it won't always work, but it'll work for most of the problems you're likely to see.